non-Euclidean rectifiability. Maybe I should mention this now. So there's going to be a dinner that Chris is organizing. So after the talk, please talk to Chris if you're interested.
Sure. Thank you, Ron, and thanks to the department for the invitation to come and visit. So it's nice to be back in New York. All right, so today I want to talk about rectifiability and sort of generalizing this from the Euclidean setting to the non-Euclidean setting. And in fact, I'll talk about two generalizations. So there will be two parts to this talk, right? But first, let's just get started with what I mean by rectifiability. So here's a definition. So we say that a metric measure space X d mu is n rectifiable for an integer n if there exists a countable family of Lipschitz maps from Borel subsets of Rn into my space X, such that, so one, they cover, the union of the images cover almost the entire space, and two, so you should think of this as like a growth condition where balls, measures of balls shrink no slower than R to the n for almost every center of a ball. Okay, so this second condition may be a little strange, but let's first, but hopefully this condition sort of makes sense, right? I mean, we're sort of thinking of rectifiable spaces as rough differentiable manifolds, except we're parameterizing them with Lipschitz maps from Borel subsets rather than continuous maps, differentiable maps from open subsets. But what is the second condition saying, right? So really it's sort of a non-degeneracy condition that ensures that sort of n-1 dimensional spaces are not n-rectifiable. So for the experts here who know what positive measure is, what I really want to say actually is that mu is absolutely continuous with respect to the positive n measure. But I'm not going to use the term positive measure in this talk anymore because it's fairly technical. Not everyone knows what it is. So I'm going to use this condition instead, which is not quite this, but has all the intuition we need. So okay, so I still have to explain what this is saying. So what can go wrong when you're parameterizing a space with a Borel subset of Rn rather than an open subset? Well, the Borel subset can be of a lower dimension, right? Whereas an open subset is fully n-dimensional. So this growth condition sort of guards us against this sort of degeneracy, all right? And sort of a good non-example to think about is the following. So consider R2 with the measure mu, where the mu measure of any set A is just the intersection of A with the line segment 0, 1 cross 0. So this is a measure on R2. It lives on 0, 1 cross 0. So I can clearly cover almost the entire space, 0, 1 cross 0, by a Lipschitz image of a subset of R2. But if I take any point on 0, 1 cross 0, and I take a ball around it, and I take its mu measure, it's bounded from below by R. So if I divide that by R squared and send R to 0, it blows up. So what I'm saying is balls in this space shrink linearly, and that's slower than shrinking quadratically, which is what I would expect to get a full two-dimensional behavior, right? So this is not two rectifiable. But actually it's one rectifiable, right? Because, I can flip this inequality on top to get that the measure of this ball is bounded by 2R. So if I divide it by R instead of R squared, then that's bounded. And of course I can cover 0, 1 cross 0 by the Lipschitz image of a subset of R. So it's one rectifiable, but not two rectifiable. Thus, this statement. Right? So you can actually generalize this to, given any rectifiable curve in a metric space, you can construct the length measure like we did before, and you can prove then that the metric space of this measure is one rectifiable. Sort of a higher dimensional analog of this are Lipschitz graphs. So you take your favorite Lipschitz function from Rn to Rm. You construct the graph in Rn plus m in the usual way. Now I need a measure on Rn plus m that lives on this graph. So here's a way to do this. So you take a set A in Rn plus m, you intersect it with the graph, you project that down to Rn, so you look at its shadow, and then you take the Lebesgue measure of that. All right? So if you use the fact that this is a Lipschitz graph, then you can easily verify that balls shrink no slower than R to the n, some constant that depends only on the Lipschitz constant. And so Rn plus m with this measure mu is n rectifiable. And finally, once you have examples of n rectifiable spaces, it's not too hard to verify that taking subsets and countable unions of these spaces end up being n rectifiable. Or by subset, I mean with the restricted metric and measure, right? So basically, once you have some examples, you can sort of cobble them together to get more examples. All right, so now that we know what rectifiable spaces look like, a question you may ask is, I mean, why do we care about them? Where do they come up, right? And, well, so remember, we're thinking of these spaces as rough manifolds, right? In which case you can think of them sort of as a regularity class of operators. And you can try to solve certain problems in this regularity class. So this has been done before for like some variational problems. And this was famously done by Federer and Fleming in their theory of integral or rectifiable currents, for which rectifiability played a very crucial role. And they used this to show the existence of minimal surfaces for a wide variety of cases in Euclidean space. Another place that they show up in analysis is singular integral theory. So it turns out that certain singular integrals behave very nicely when you pair them with a rectifiable measure in Euclidean space. So, for example, principal values can exist. There's also a strengthened notion of rectifiability called uniform rectifiability, for which certain singular integrals behave even better in that they can actually define bounded operators between LP spaces. So I think this was first done in the work of Calderon when he studied Cauchy integrals on Lipschitz graphs, and it has subsequently been developed by a wide variety of people, and these are just some of the people who've made very important contributions in this theory. Okay, so here's some analysis. What about places it may show up in geometry, right? Well, okay, so again, we're thinking of these as rough differentiable manifolds, and this can actually be made a little precise. So it turns out that limits, Gromov-Hausdorff limits, of certain Riemannian manifolds can give you a rectifiable space despite not being, the limit not being manifolds. So, for example, Cheeger and Colding showed that Gromov-Hausdorff limits of Riemannian manifolds with Ricci curvature bounded from below end up being rectifiable, right? And finally, just philosophically, why do you like rectifiable spaces? Well, they sort of give you a dimensionality to your metric space, right? So, for example, you could have an n rectifiable measure in Rm, and like m could be much bigger than n. In which case, okay, your ambient dimension is huge, but what n rectifiability is saying is somehow that all the important stuff is happening on an n-dimensional level. So, I mean, it's just sort of another reason why we care about rectifiability. Okay, so now that we see how these things come up, the first question we're going to be dealing with is the following. How can we tell if the space is n-rectifiable, right? So, given a metric measure space, I want some condition that will tell me if my metric measure space is rectifiable. So before I tell you the answer to this, in Euclidean space, I'm going to recall a definition. So for a metric measure space, we say that the n density of the measure mu at a point x is the following limit if it exists. You take the measure around of a ball around x of radius r, you divide that by r to the n, and you send r to 0. So it sort of measures that sort of infinitesimal growth or decay or whatever of your ball around x compared to r to the n, all right? And it's a limit, so of course it need not exist. But David Preiss characterized rectifiability in Euclidean spaces using the density. So he proved the following. So you have a radon measure on Rm. Then Rm, the Euclidean space, with this measure is n rectifiable if and only if the n density exists and is positive mu on the circular. Okay, so this pointwise condition guarantees rectifiability of radon measurements on Rm, and it's a complete characterization, right? So, okay, so this is a fairly complete answer, which is great, but when you look at this theorem, you may sort of, I mean, for a little while, you may think about the following thing, which is, so we said before that in the definition of density, it makes sense for a general metric measure space, right? You just need a notion of what balls are and measures of balls. So at least you sort of state this for the general case of for a metric measure space. So is it true then? So what if we're dealing with some metric space that is not Rn with the Euclidean metric? Is this statement still true? So there are two directions to this. In the forward direction, it was shown by Kirchheim that yes, it is true. If you have an n-rectifiable metric measure space, the n density exists and is positive in almost every way. In the backwards direction, it's not true. And there's actually a fairly simple counterexample to this. So consider the von Cox snowflake, which is R with the square root metric and the normal debate measure on it. Right? So the square root makes it non-Euclidean. Now, it's very easy to verify that the measure of any ball of radius r is 2r squared. And so if you divide that by r squared, it's always 2. So in particular, the 2 density exists, and it's constantly 2. But it's not n-rectifiable for any n. And here's sort of an idea of the proof. So consider a Lipschitz map from an interval AB with the usual metric into my space X. Now if you just play around with what it means for this function to be Lipschitz, so meaning you square both sides, you get that this map is essentially a two-holder function on AB. And we know two-holder functions on AB are constant from just first-year analysis. So once you know this is true, the same then also holds for any Lipschitz function from a Lipschitz path-connected space into my space X, right? Because you take any 2 points in your domain, you take the Lipschitz path between the 2 of them, you look at the function restricted to this path, it's constant, so everything gets collapsed to a single point. So in particular...
So is a Lipschitz path different from just a rectifiable path?
It's the same. Yeah, I will interchange Lipschitz and rectifiable path. Same thing.
You're using that because every rectifiable path is a Lipschitz image of an interval?
Yes. Okay. So Rn is a rectifiably path-connected space. So any Lipschitz image, so the Lipschitz image of any Lipschitz image of Rn into my space X is a single point, which has measure 0. And so I can't cover this space by a countable union of measure 0 images. So it's not rectifiable. All right? For any n. Now, I mean, this isn't a foolproof because in our definition of rectifiability, we're talking about parameterizing our set with Lipschitz images of Borel subsets of Rn, which need not be connected. But you kind of massage this a little bit, you just effectivize it, and then sort of it'll go through. The main part, the sort of main part of the proof is already through.
So the other part, the forward direction, that was true.
That is true.
Is that sort of morally the same as something like Rademacher's theorem?
Right.
Lipschitz functions have derivatives almost everywhere? Because you're parameterization.
Yeah, Kirchheim essentially proved a Rademacher's theorem from Rn into a metric space X, where he just showed that if you take the pullback metric of this function on as a metric on Rn, and you sort of blow up the metric, it converges to a semi-norm. And then that's enough to sort of make all the usual things work. Okay, so we're missing something, obviously, if we want to generalize Preiss's theorem. And it turns out that the missing ingredient is differentiability. All right, so now I have to tell you what I mean by differentiating a function on a metric space. But before I do that, let's just recall what I mean by when I say that a function from Rn to R is differentiable at a point x naught. That simply means there exists some linear transform from Rn to R such that this linearization happens. Right? So this is just Calc 1 or Calc 3, depending on how you teach it. But okay, so now let's take a metric space, and I'm going to need an auxiliary function phi from x to Rn. We'll call it chart. So we say then that a function f from x to r is phi differentiable at a point x naught in x if there exists some linear transform from Rn to R so that the this kind of linearization happens where we have to take the difference between x and x naught after we push forward into Rn by phi. Okay? Because this is the only way we'll get an affine behavior on which we can apply our linear transform. So this looks a little confusing. Just consider the case when x is Rn and phi is the identity map. All right? In which case phi of x minus x naught, phi of x naught is exactly x minus x naught, and we see then that this becomes this. So we're really generalizing the chart that we're differentiating a function with regards to. Right? So this was this notion of differentiation was introduced by Cheeger, and so we call dfx naught the Cheeger derivative of f at x naught. Okay, so this is just a definition. There's no reason a function on a general metric space has to be differentiable with respect to anything. So we're going to instead concentrate on a class of metric measure spaces, for which we have a very rich differentiability structure. All right? So we have the following definition. So a metric measure space xd mu is an n-dimensional Lipschitz differentiability space, or LDS, if there exists a Lipschitz chart so that every Lipschitz function from x to r is phi differentiable mu almost everywhere. All right? So in other words, these spaces are precisely the metric measure spaces for which Rademacher's theorem holds for this generalized notion of differentiation. Where, of course, here, phi should be independent of f. Right? So, again, this is just
Is
a
phi dependent on?
It's dependent on x.
On x.
On x.
The
Oh,
space
sorry.
x.
On the space x.
Because in your other definition, you had this point x0, and in principle, you could imagine you go to different points, you need different phi.
Well, actually, if you go to different, yeah. Well, you can always use f itself as the, or actually, never mind about that. But yeah, in theory. But here, there's one that works for almost every point, essentially, right? And for every function, and for almost every point. It's a very special function, all right? It's not any function will have this. Okay, so this is again just a definition. So you may be worried that there's no good example. This is a trivial class of measure spaces. That you could be worried about that, but it's not actually. So examples include Euclidean spaces. By what we just said, if you take phi to be the identity map from Rn to Rn, then Rademacher's theorem immediately tells us that Euclidean spaces are differentiability spaces. I'll talk about Carnot groups in the second half of this talk, so I'm going to sort of brush by this right now. But Hansu proved that these are differentiability spaces. And more generally than these two, doubling metric measure spaces with the Poincare inequality were proven to be differentiability spaces by Cheeger. And these spaces, there are many very exotic examples of such spaces constructed by many people. And it includes the previous two cases. So all of this is just to say that this is not a trivial class of metric measure spaces. Right? It contains a very rich class of spaces for which there are very non-trivial, non-Euclidean behaviors. And I should say that I'm doing Cheeger a disservice by just saying this as an example. It's really a theorem, right?
So for example, if you take the unit disk with the hyperbolic distance.
That's not doubling.
It's not doubling. Right?
It's not doubling.
But I'm asking, is that that is not an example? I mean, that doubling is just one class.
It is. It should be. I think it's asymptotically doubling. I mean, locally, it can be parameterized by Rn. I mean R2, right? Yeah. So so you can just.
But that was my question about whether you can use a single chart for the whole space.
No, okay. So usually in the definition of this, we preface this by saying there exists a countable decomposition of our space into pieces such that this holds there is a chart for each piece.
Okay.
I'm ignoring all this decomposition.
So then for this thing, the unit disk with the hyperbolic distance is not an example.
For this one, no. But yeah, if you just decompose it, then locally, of course.
Yes.
Okay. And I will say that in some ways, this is sort of the right class of metric spaces for which this holds. But that's another talk. I just wanted to mention that. But okay, so these are very non-trivial, very nice metric spaces with a lot of differentiability. So now that we know what I mean by differentiating a function on a metric space, we can state our characterization of rectifiability. So this is joint work with David Bate. We showed that a metric space is n-rectifiable if and only if there exists a countable number of Borel sets that cover almost my entire space X, so one, the n density of course must exist and be positive mean almost everywhere. So this doesn't depend on my decomposition. But two, each of these Borel pieces with restricted metric and measure is an n-dimensional Lipschitz differentiability space. All right. So this is if and only if. So the missing ingredient was precisely differentiability. As soon as we have that, we get a complete characterization. One quick remark. So both 1 and 2 of this are necessary. Both of these conditions are necessary, and they do not imply one another. So if you're trying to get by with just one of these, you're going to have, you can construct counterexamples. Okay, so how does one prove a statement like this? So let's go back to the definitions.
Okay. So you have this almost everywhere statement, right? So do you know what happens when that doesn't hold? So what kind of loci do you have where that doesn't hold? Is that
This one?
number one?
This one.
Even in the Euclidean case?
I mean, it could be 0.
Any set of measure 0.
Yeah, yeah, right. Like go back to R2 with the strip that we concentrate all our measure on. You take any other point outside the strip. I mean, any small enough ball around it will have measure 0.
So anything can happen.
Yeah.
Well, and anything happen, I thought characterizing the non-differentiable sets of a Lipschitz function was a difficult problem. Or I'm mixing it up with something else. Aren't there like null sets which contain a point of differentiability of every Lipschitz function?
Yeah. Well, it depends on the dimension of your.
There's some subtleties involved.
Yeah,
Set measure 0.
I mean, yeah, like for that, that's purely in the Euclidean. I mean, like we have nowhere the technology to handle that in metric spaces. So yeah, like it measures 0 sets.
So the question of what happens on the sets of measure 0 is not completely exploded. Even in the Euclidean setting, there are very subtle questions.
So even in the plane, this is a very hard question that has a theorem about it that's not fully written down.
Okay.
So Lipschitz functions are differentiable almost everywhere, but we don't quite understand the sets that are not differentiable. Is that fair?
Yeah. Okay. So all right. So we're trying to prove this, and let's go back to the definitions of rectifiability and differentiability. All right. So if you remember, rectifiability says something like, there exist Lipschitz maps from Borel subsets of Rn into space X such that something happens. And differentiability said there exist Lipschitz maps from Borel subsets of X into Rn such that something happens. So, I mean, if you just play around with the definitions a bit, and you sort of set them in front of you, you'll see that we're essentially done if the phi's and fi's are by Lipschitz. So if you don't know what by Lipschitz means, it just means that they're Lipschitz and they can be inverted in a Lipschitz way. Because you just take your fi's, you can invert them, and then you'll get a phi, and vice versa. So that's great, except for the fact, of course, that not every Lipschitz function is by Lipschitz. Like the constant function is not by Lipschitz. So we're going to need some more general notion of being by Lipschitz. And this brings us to the following definition. So we say that a Lipschitz function from X to a metric measure space Y nu is by Lipschitz decomposable if there exists a countable number of Borel sets EI of X, such that the restrictions on these EIs are by Lipschitz. And, okay, so I'm not saying that EIs cover almost all of X. So there's a junk set left over. But this junk set, I require that its image has new measure 0. So the second condition may seem a little strange, but hopefully the first condition makes sense, right? We have this large Lipschitz function, and we're just taking by Lipschitz pieces out of the function. But what does the second condition say? Well, I mean, why is it here? Well, okay, so the type of statements people usually try to prove is the following. Given some very specific x and given some very specific y nu that people are interested in, they want to prove that every Lipschitz function from x to y is by Lipschitz decomposable. Now, if you look at every Lipschitz function, you have to look at constant functions. And constant functions have none of these EIs, right? Because no restriction of a constant function is by Lipschitz. But constant functions have, so your entire junk set is the entire domain. But we're saved because a constant function has a one-point image, and under mild assumptions on nu, that has measure 0. So essentially, we're modding out by the constant functions, what this is doing, right? I mean, other than this most degenerate of cases, which must happen if you consider all Lipschitz functions. We're saying, other than this, everything else is fine.
So this is the
Forcing
reversing
like Sard theorem.
Sard's theorem.
Exactly. It's very much a Sard's theorem.
You're sort of saying assume Sard's theorem hold, that's your definition.
Sort of. Yeah. Exactly. Okay, so, but you see that this is sort of the right notion of being by Lipschitz that we want, right? Because we didn't need that our big parameterizing map, for instance, was by Lipschitz. We just need to be able to decompose it into a countable number of by Lipschitz pieces. We pass to them, and then we can invert them to get our fiats. So this is what we actually want to show. Okay, so in one direction, Kirchheim already showed that it was true. So for these parameterizing maps in an unrectifiable metric measure space, he showed that each of them are by Lipschitz decomposable. So in other words, if you're a rectifiable space, you are a differentiability space. That's the direction that he proved. Right? Although when he proved it, obviously the definition, the technology wasn't set up to state that, but that's what he showed. Okay, so what David and I did was we showed that each of the charts for a differentiability space is by Lipschitz decomposable when you have the density condition, right? And actually we needed that all of these by Lipschitz pieces cover almost our entire domain, which actually, which really required that the fact that these differentiability charts are very special functions. Like they can't be constant functions, right? Because a constant function obviously does not satisfy that. But at the same time, you shouldn't expect a constant function to be a differentiability chart because it can't capture any first order fluctuations of any Lipschitz function. So, okay, so sort of special properties of the phi save us from this. Now, this is sort of where I'll leave it because to get into why these are special functions, it's going to get far too technical for this talk. So let me just recap by saying that for Preiss's theorem, we generalize, it's generalized from the Euclidean setting to the non-Euclidean setting as soon as you add differentiability. Okay? Okay, so that's the first sort of result. Are there any questions? Okay, so now we're going to talk about another generalization where we're generalizing now, we're going to generalize the parameterizing space that we're using. So we've been parameterizing space using Rn. Now we're going to use something more general. The object we're going to use is the Heisenberg group, which is just the Lie group R3 with a special group product where you see in the first two coordinates, it's the usual group product. Then the last one, there's this twist to it. It's the cross product of x and y. And this twist makes it non-abelian. The identity is still 0. And the group inverse of a point is still minus that point. So I'll explain in the next slide why I view this as a generalization of Euclidean space, even though it's clearly not Euclidean. So that's coming. But first, let me tell you what the metric and the measure of the space is. So to define the metric, I'm going to first define a norm on my space. So the norm of a point x, y, z is going to be the maximum of absolute x, absolute y, square root absolute z. Now, given a norm on my space, I can define a metric in the usual way that one would for a vector space. You take 2 points, g and h. You take the group inverse, you take their displacement, g inverse h, which is the right displacement, and you take the norm of that, and that will give you a left invariant metric. All right? And the measure, I'm going to keep that to be the Lebesgue measure on R3, which turns out to be a hard measure. Okay, and so one more thing. So for every lambda greater than 0, we can define a scaling automorphism that sends x, y, z to lambda x, lambda y, lambda squared z. So why do I need the square here? You can see that in the group product, if I multiply x and y by lambda, I get a lambda squared term here. So in order for this to be a homomorphism, I will need a lambda squared scaling in the z factor. Okay, so now I'm going to list some geometric properties of the Heisenberg group. I'm not going to justify them. It's not so important that you know why they're true. It's simply important that you know that they are true. But once you know these properties, most of these are 2-3 line exercises. So, all right. So let's just go through these properties. All right. So the Heisenberg group is still topologically R3. It's geodesic. Okay, so this is not completely true. It's what's known as quasi-convex, meaning between any 2 points there exists a rectifiable curve of length no more than, let's say, 1,000,000 times the distance between the 2 points. So this curve may not achieve the distance between the 2 points, but it'll achieve it up to some multiplicative constant. But for our purposes, you really lose nothing by thinking of it as just geodesic. Left translation is isometric. This is simply because our metric is left invariant. The scaling automorphism scales the metric in that the distance from lambda x to lambda y is equal to lambda times the distance from x to y. Just look at how the scaling automorphism scales the norm to see that. Left translation is measure preserving. And finally, the scaling automorphism scales the measure by lambda to the 4th. So taken with the fact that left translation is measure preserving, we can see that the measure of any ball of radius r in the space is some universal constant times r to the 4th. Okay, so why did I tell you these properties? I told you these properties because if you look at them, they all hold for Euclidean space, or like a finite dimensional norm vector space, right? So it's almost Euclidean, except that it is non-abelian, from what we said before. And it's actually a corollary of a theorem of Lazan that as soon as you add being abelian to this list of properties, you get a Euclidean space. All right? So
wouldn't the power be?
Yeah. Okay. So yeah, this should be 3. So as soon as you add being abelian to this to 1 through 4, you'll get a Euclidean space, and that will force this to be 3. So yeah, we're just sort of sweeping that under the rug. Okay,
So if you were to allow that to be an arbitrary power, would it always turn out to be an integer on the other axes, or no?
Yeah. By the main theorem of Ladan, that would necessarily have this be an integer. Okay, so we'll call group metric spaces satisfying 1 through 4 Carnot groups. And so we see then that, well, here it's any Rn, not R3. But so you see that Euclidean spaces are precisely the abelian Carnot groups. And so the Heisenberg group is the simplest example of a non-abelian one. And so this is why we're thinking of the Heisenberg group as a generalization of Euclidean space, because it's a non-abelian version of it. All right? So once we're thinking of the Heisenberg group in this way, we can sort of use it to come up with notions of rectifiability, right? So here's sort of the naive definition we would come up with. So we say that a metric measure space x d mu is Heisenberg rectifiable if there exists a countable family of Lipschitz maps from Borel subsets of the Heisenberg group into X, such that, so the union of the images cover almost the entire space, and 2, balls shrink no slower than r to the 4, where this 4 here comes from this 4 here. Okay, so this is some class of metric measure spaces, and we would like to know what geometric properties these spaces have. So the question we're going to be dealing with is the following. Are the parameterizing maps here by Lipschitz decomposable? So remember, Kirchheim proved that for Rn rectifiable spaces, these maps were by Lipschitz decomposable. And what was the upshot of this statement? That means you can take these FIs, these countable number of FIs, Borel decomposed them into another countable number of by Lipschitz maps, FGJs, and then, you can pass so therefore in the definition, you can just pass to these by Lipschitz maps instead, and everything still works. So basically, we can replace this Lipschitz with by Lipschitz without losing anything when you're talking about Rn rectifiable spaces. So this is why we're interested in the question of whether or not these FIs are by Lipschitz decomposable. All right? So let's first consider the case when my space X is just the Heisenberg group itself, in which case Scott Paul has proved that Lipschitz maps from the Heisenberg group back into the Heisenberg group are by Lipschitz decomposable. And in fact, we know something even more. So for any delta greater than 0, there exists some m of delta greater than 0 with the following property. So for every one Lipschitz function from the unit ball of the Heisenberg group back into the Heisenberg group, there is a Borel decomposition of the domain into m pieces, where m is no greater than m of delta, and a junk set Z, so that f restricted onto each of these EIs is by Lipschitz, and the measure of the junk set and the image of the junk set has measure less than delta. So this is some quantitative decomposition theorem, right? Because rather than saying your junk set has image measure 0, it's bounded by some delta, and with that you get quantitative estimates on the number of by Lipschitz pieces you need. So, so all of this is just to say that, I should say that this was initially proven by Meyerson for certain Carnot groups to other Carnot groups, and I generalize this to all Carnot groups to all Carnot groups. But okay, so we see that if our target is the Heisenberg group itself, then we have very nice decomposition properties. It's quantitative. But that still doesn't tell us anything about Lipschitz maps from agent 2 of just a metric measure space X. Let's say that space X is still Heisenberg rectifiable. All right, so what about this case?
Can you give some kind of intuition of what's the difference between Heisenberg, this property for Heisenberg and for R4? So R4 rectifiable and Heisenberg rectifiable. Is there some intuition that says they're so different?
Well, so it turns out that there are no by Lipschitz maps between. There's no by Lipschitz embeddings from the Heisenberg group into R4 or vice versa. So, somehow Heisenberg group has sort of, its rectifiable curves are sort of they sort of have to, there's essentially 2 directions of rectifiability in the Heisenberg group that sort of that sort of generate the entire space that you can get to. Whereas in R4, there are 4 directions of rectifiability, X, Y, Z, and W, if you want to call that. So, this sort of mismatch of dimensions sort of gives you a collapse between the 2 geometries. That's sort of very vague. But
perhaps you should mention the word sub-Riemannian.
Yes.
It might make sense to some people who used to
the
deal with
metric
Riemannian geometry.
Is the metric you put on these spaces the Carnot-Carnot-Liouville metric, or is it?
They're not, but they are by Lipschitz equivalent
Okay.
to that. So
you still have the horizontal.
Yeah. That's right. What we're saying here, essentially, if you know sub-Riemannian, here we're saying x, y have rectifiable directions and Z does not.
I don't know if people know sub-Riemannian, but I'm sure they know what Riemannian is. Probably much better than I do. But
Yeah.
it's sort of like Riemannian manifolds, but they're degenerate directions where the local known collapses. It's zero basically in certain directions.
Yeah, but somehow by like the
Draw a helix in 3 dimensions.
Yeah. Like you can trap
Little black board.
Oh, okay. All right. Right. So somehow.
It's very far
Yeah.
away.
Yeah. So somehow, like
You can't go straight.
by the distribution of this tangent subbundle, by the twist of the distribution of this tangent subbundle, you can connect a point to a point directly above it, even though going up is not in.
Going straight up would be infinitely far, but
Right.
making like a helix would be finite. Is that correct?
Right. I mean, yeah. Essentially, you have a space
much
of
longer than you would expect.
Yeah, you have like a distribution of tangent planes that allow you to connect points by going along the subbundle. All right, and that's sort of the mismatch in dimension. Okay. All right. So it turns out, okay, so we want to know whether or not such spaces where X is, let's say, a Heisenberg or rectifiable metric measure space are by Lipschitz decomposable. And it turns out that they are not. So before I say anything about that, let's just recall that the metric measure space is all force S regular if balls of radius R have measure approximately R to the S, up to some multiplicative constant. So the Heisenberg group is 4 regular in particular. Okay, so we have the following theorem joined with Enrico Ladon and Tapio Rayala, who show that there exists a 4 regular metric space XD mu and a Lipschitz surjection from the Heisenberg group into space X, for which the restriction of F on any positive measures subset of the domain is not by Lipschitz. Now, it's not too hard to prove that that Lipschitz maps between 2 4 regular metric spaces like we do here must send measure 0 sets to measure 0 sets. You just take your measure 0 set in your domain, you cover it by a lot of really small balls, those get sent by your Lipschitz map into a set contained by comparatively small balls, and then you use your all force regularity estimates to bound the volumes. All right, so with that remark, we then have that this function cannot be by Lipschitz decomposable, right? Because what are the only subsets on which the restriction can be by Lipschitz? Those are measure 0 sets. But those then get sent to measure 0 sets in the image by what we just said, and so we can't cover this again. So we can't cover this by countable union of those because it has positive measure, and so it's not by Lipschitz decomposable. Okay. So all right. So let's sort of see how one might construct such a space in surjection. So so let's first recall that the norm in the z direction behaves like the square root. This is just in the formula I gave you. And it's not hard to verify that the center of the Heisenberg group is the z-axis. It's just algebra. And so you see that H of course is foliated by cosets of the center, and along the center the metric behaves like the square root, so it's foliated by copies of the snowflake. Now, the triangle equality for the square root metric is usually very generous, by which I mean you take 3 very spread out points, then the distance from A to B plus the distance from B to C is usually much greater than the distance from A to C. This is just by subadditivity of the square root. Okay, so now what is this metric space in this Lipschitz surjection going to be? The metric space is going to be the Heisenberg group with a different metric that we're going to explicitly construct. And the Lipschitz surjection is just going to be the identity map between the Heisenberg group and this new metric. So I just have to tell you how to construct this new metric, right? And what we're going to do is we're sort of going to manually push together vertically separated points in many locations and scales in a very careful way. So if we do it enough so we're not actually going to identify these 2 points, we're just going to push them closer to each other more and more. So if we do it in enough places and scales, then you can see we have no by Lipschitz pieces because the inverse would have to spread them out a lot, which would get less and less Lipschitz. But we're also going to take advantage of the slack in the triangle inequality to show that if we are careful enough, the Lebesgue measure on R3 with this new metric is still going to be 4 regular. Okay, and again, it's very technical how you do this, so assuming you can do that, you get exactly the metric that you want, and the identity map is exactly what you want it to be. So that's sort of just like a broad stroke of this proof. But you see,
So is this metric sort of constant on planes parallel to x, y? It's only a function of the height?
yeah, like it'll.
Or are you doing different things?
You sort of take 2 points and you sort of just pull them together, like in a way that the in-between points don't get pushed together. You sort of like, you can imagine pulling them out of the Heisenberg group, like stretching them out and then just manually putting them close together and then going into the metric and adjusting everything to account for that. And you're doing this just vertically, all right, at many locations in space. So yeah, you're leaving horizontal undisturbed.
You're sort of building some kind of like singular function in the vertical direction like that. Cantor staircase, except it's going to be tilted
Yeah.
so you're not actually collapsing volume.
Exactly. Something like that. Okay, so that's sort of the broad strokes of this. I will say one more thing before we move on, which is, okay, so why were we interested in this question? We were interested in it because if it is bi-Lipschitz decomposable, then I can replace this Lipschitz with bi-Lipschitz. We just showed that this is not bi-Lipschitz decomposable, but that, of course, does not imply that we can't replace this Lipschitz with bi-Lipschitz. And it's true by the statement, by the theorem I gave you, we can't do that. It turns out that with a further analysis done, you can show indeed that with that same metric space there, you cannot parameterize it with bi-Lipschitz images of subsets of the Heisenberg group. So that requires a further analysis that was done in the same paper, but we get this like strengthened. So that's an example of a Heisenberg rectifiable space that is, let's say, Lipschitz rectifiable, but not bi-Lipschitz rectifiable. So that's very different from the Euclidean case. Right? So we get very different behavior. Okay, now some open problems. Okay, so I said, so before I've made an effort not to say Hausdorff measure in this talk, but it's not going to be possible anymore for open problems. So for those of you who don't know what Hausdorff measure is, I mean, I guess you can learn it and then come back and think about these. I'll say one thing about it, which is the Hausdorff measure can be defined for any metric space. Like you can define a Hausdorff S measure for any positive S for any metric space. It really just requires a metric. Right? And the S sort of gives a dimensionality to this measure. So hopefully you can try to grasp onto that, maybe. Okay, so the first question is the following. So before Preiss's theorem, Mattila proved the precursor, which said that, so for if you take any Borel subset of Rm, and you look at Rm with a restricted Hausdorff n measure on E, he showed that this is n rectifiable if and only if the n density of this restricted measure is 2 to the n for almost every point with respect to this restricted measure. And let me just say here, the 2 to the n, this is from a non-standard normalization of our density. Right? Usually you'll see 1 in the literature, but that's just normalization issues. So you look at this, and I just told you that Hausdorff measure makes sense for any metric space. So of course then you can ask the same question as we did in Preiss's theorem. Does this work when we have a non-Euclidean space, but equipped with the Hausdorff n measure? Right?
So I don't quite understand the relation between Mattila's theorem and Preiss's theorem. Is this a special case of Preiss's theorem?
Yeah. So this is when you're looking at this you had
a mu, and now you have a particular mu defined.
Yeah. His was the radon measure. This is now a very specific restricted Hausdorff n measure. So it is a bit, but you get more, right? Because you get a very specific density.
It came before.
It came before, right? Okay. So therefore, we have to give this condition on this space is equivalent to n rectifiability. And of course here we don't want to mention, we don't want to reference differentiability at all, because as soon as we do, we're done by previous statement. So one way to maybe attack this problem is to ask if this condition here, so a very specific measure having a very specific density gives you differentiability. Right? That's one possible way to attack this problem. But I mean, as far as I know, this is wide open, except for the case when n equals 1, in which case Preiss has a proof that this is true. But 1 is very much easier than the general case problem. Okay, a second question is the following. So, so remember, we're looking at Carnot groups as non-abelian versions of Euclidean space. So for any Carnot group H, we can come up with a notion of H rectifiability. You just have to calculate a certain power of growth of balls. So then you can ask if there's a Preiss theorem for H rectifiability of Radon measures in G, where G and H are both Carnot groups. So remember, Preiss's theorem characterized n rectifiability in Rm in terms of the n density. So here, almost surely you're going to need something more than the density. I mean, what else do you need, right? And we don't really know. Scott Pauls has some partial results, but they're very not tight. And okay, so finally, and this is sort of the most amorphous question of them all. So what nice all-force n-regular spaces X besides Rn have the bi-Lipschitz decomposition property for all Lipschitz maps from X into arbitrary metric spaces Y with the Hausdorff-Fed method. So I'm hiding some technical things behind this nice, of course. But I mean, the reason we're interested in such a problem is because if we have such a space, then we can come up with a notion of rectifiability based on X. And remember, once we know that these Lipschitz maps are bi-Lipschitz decomposable, we get some very nice properties. So this was asked at least 15 years ago by, I know David and Sems asked this. And they asked if the Heisenberg group was an example of such a space. But we saw, I mean, because it was sort of a very natural candidate. But we saw that the Heisenberg group is not an example. And now I can't really, there's no other natural candidates that come to mind for me. So it could be that Euclidean spaces are precisely the metric spaces for which, metric measure spaces for which this holds, in which case that'd be a very nice theorem, but I mean, we don't know. So this question is really getting to the heart of trying to come up with a non-Euclidean version of rectifiability, and it's wide open. So
it seemed like the main bad thing about the Heisenberg was that distance is essentially given by a sub-Riemannian stuff, not a Riemannian stuff. And that's why the dimension grows. You have to go really, really a long way to get to points that look nearby in the Euclidean geometry. So don't you expect, if you had a metric that came from a Riemannian metric on any manifold, that you would be able to?
Yeah, but Riemannian metrics are essentially Rn.
Okay, so you're talking, this question is locally, not...
Yeah. It should be, I mean, it should satisfy certain like invariant, like rescaling. There should be some symmetries to the space that I'm hiding under nice here. I mean, essentially spaces that look like Rn, like rectifiable spaces or Riemannian manifolds, should all be contained under the umbrella of Rn.
Because the way I read your bi-Lipschitz definition is that it's like a Lipschitz version of the definition of a manifold. That you actually have an invertible transformation that locally maps the thing to something that looks like Rn. So I would expect, I mean, if that's what, I didn't understand that this was local. So if you're saying locally.
I mean, basically locally an X rectifiable space should, by Lipschitz, look like X. Right. I mean, there are some reasons to believe that Rn may be the only one. I mean, again, essentially Rn. maybe the only one. But those are far more just like a vague feeling right now than any kind of real concrete, actionable kind of, propositions. So, but yeah, so this is still fairly open. Okay, so that's all I have. So thanks.
Any more questions or comments?
Yeah. Do you know if the spaces that support like a doubling measure have to be this Rn? I mean, in Cheeger, you mentioned that Cheeger example, but that also has a measure, the measure that's doubling. Do you know if any space that supports a doubling measure automatically has to have this by Lipschitz property, or it doesn't have to be local?
I mean, like, the only examples we know where you have this property is Euclideans, or spaces that locally look like Euclidean space, that are essentially rectifiable spaces, right? Like, that's what...
So is that question pretty close to your third, the question I asked pretty close to your third, or a special case of your third question?
I think so, yeah.
Can you move that one slide?
Yeah, like, I mean, well, you automatically have doubling from the fact that this is offers and regular. But I guess, like, a rectifiable space need not be doubling, right? You can sort of, hyperbolic space. But, everything is local.
But this is a local, all this stuff.
All this is
now
local.
I understand.
Differentiability is also local, right? It makes sense that it's local because you're only looking at the infinitesimal. So this is why differentiability and rectifiability, you should expect it to sort of, or I don't know if you expect, but you shouldn't be surprised too much. Everything is local.
This example that you have with Ladon and Ryla, is that doubling?
Yes, it's all first order.
I had sort of two almost philosophical questions. Maybe I'll just ask them both. You can choose whichever one you want to make it easier. First of all, I guess I'm mentally thinking of the Carnot groups as like a step between like Euclidean analysis and maybe Lie groups.
Mm-hmm.
But I don't know if it's a baby step or a big step or how much more complicated that would be. And then the other thing was, one of the motivating examples you mentioned was like minimal surfaces in the development theory of rectifiability. And I was wondering if there were some applications or some goal or something that doesn't mention rectifiability but awaiting the technology to be developed, then that could be attacked, something about groups or boundaries of groups or this or that. Or I know it's interesting on its own, but I didn't know if there were if you weren't interested in rectifiability, some reason why you'd be forced to learn about it eventually because it's on its way to solving some other problem.
Okay, so your first one, I think it's not a huge step from Euclidean space to these spaces because of all these geometric properties I just mentioned to you. But there are some very non-trivial differences that make, for example, this much harder. Like for example, like the growth of balls does not uniquely characterize Carnot groups the way they do for Euclidean spaces, right?
Mm-hmm.
If you grow like R to the 4, you know you're R4 if you know
So you
you're
can have multiple degenerate directions and non-degenerate.
Yeah, and also one very crucial ingredient about Euclidean spaces is that their subgroups decompose very easily, right? Whereas Carnot groups is not true at all. So that's so it's I think it's closer to, or I don't know, I don't know too much about Lie group theory, but yeah, like it's not that close to Euclidean space, but there's a lot of intuition you can use to try to develop something. The second one, I guess like the only one I can really think of, it's mainly these problems in analysis where it comes up because you're forced to relatch. We try to prove something with regards
What
to...
other questions about, on what spaces a singular interval going to be bounded on, or things of that form, or what's the best version of the Rademacher theorem on differentiation?
Right.
Things like that. I think everyone appreciates minimal surfaces being like really interesting, soap bubbles and stuff, and then you have to invent, metric measure theory to sort of like attack that problem. I didn't know if there were.
Well, there is that. I mean, it was used by Shushang and
Let's ask Blake.
this theory, like, it gives you, this work of Cheeger and Holding was used by these guys to get, you have these limits of spaces that a priori could be horrible, but this theory tells you that they're basically extremely nice spaces.
Okay.
Yeah. So like you're looking. I mean, I think like anytime you have like a limit of things, or you want some compactness, right? This is sort of where you go. This is where this comes in because it allows you to relax your problem so that you get a solution. And I mean, getting compactness is required in a lot of places. So I mean.
It's when you mentioned this variational calculus. That's precisely the point.
Yeah.
If you want to take limits in these spaces of extremely irregular objects, they won't be closed. So this theory comes up when you construct closures of extremely irregular objects.
More questions?